I'm Abhi. Just a bit of introduction about myself. I work at Elastic, the company that makes Elasticsearch search engine or vector database. Some of you might have used that product. I started there about a month ago. Prior to that, I have a lot of experience in the area of NLP, generative AI. Prior to that, I was working for a Canadian internet content publishing platform, Wattpad. Anyone has heard of that company? Cool. Two people. That's great. So as I said, in this session, we'll explore some of the strategies for scaling RAG systems. And I know RAG is a pretty popular topic, still relevant in the age of agents. So so we'll be focusing on some of the critical challenges when it comes to RAG. Challenges like latency, scale, how to optimize your RAG pipeline without going bankrupt. That's an important factor when you scale your RAG system. And this workshop will be divided into two parts. So first we'll start with a theoretical overview of these different strategies, and then we'll have a hands-on coding session at the end of it. So before we begin, I want to clarify a couple of important points. Most of the techniques that we'll see in this workshop are universal. That means that you can apply them to any RAG pipeline. So if you already have a RAG in production or you're working on it, most of the techniques will be applicable regardless of the underlying technology stack. And I may use some examples like for vector database, Elasticsearch, or for models, Hugging Face, but those are for demonstration only, and the principles are transferable. And finally, the objective of this talk and the workshop is to focus on these optimization strategies and principles. It's not to compare any products with each other and specific solution providers. Okay, so with that out of the way, let's start where most people or teams working on RAG or some kind of a retrieval system start. So it's usually they begin with some kind of a prototype, and just a raise of hand, how many of you in the room have a RAG pipeline in production or are tinkering with that idea? Okay, good bunch. Anyone has agents in production? Okay, cool. So as I was saying, for those who here have experience in productionizing RAG pipelines or are working on that, I usually call this whole experience as the RAG dream. It usually starts with a spark of an idea from management, could be your idea, where it goes like, okay, what if I could connect an LLM to my proprietary data, to a database, to Salesforce, to any other kind of connector. You spend a few days, maybe a week building it out. You hook up documents, you hook up a vector database, write a bit of Python or like any other programming language, and then it's a magic moment where you see, okay, it's working. You may ask a question about find me the information about customer ticket, or you may use it for a SQL, text to SQL kind of scenario, and it gives you decent answers. The next step would probably be that you would want to showcase this to your team, your manager, and call it a successful prototype. But what happens next? When you have something working, how do you actually scale it from a couple of users from your team to millions of users that might be applicable in some scenarios? And this brings us to the reality check. So I want to start by sharing a quick story from my last organization. Around late 2023, when we were figuring out our first RAG use case, we also started with a RAG demo. And it was for conversational search experiences. So it was a platform for finding stories similar to Netflix, and we wanted to provide a conversation search experience to our users. So the idea was pretty simple. Users will provide a conversation, a search query, and the system should be able to figure out what are the most relevant stories for that user. And we started with a very simple prototype, as you might saw in the previous slide, and quickly got to the wow moment that, oh, it's working. Everyone loved it, but when we started implementing it in production and during testing, we kind of confronted what you can see here as a three-headed monster. First, there's this challenge of cost. Like, why is the cloud bill so much? Like, we have to embed millions and millions of documents, running a large vector database instance 24/7, making API calls to not only vector databases but to LLMs. All of this cost add up, and it can quickly go from tens of thousands of dollars to even more in some extreme cases. And the question became clear, like, is this financially sustainable? Can we have a naive RAG solution in production? Then we also encountered some other issues like latency. So we have this system, the prototype works well, but what about SLAs? Our customers expect the answers in, let's say, less than a second, or maybe even less than that in some cases. So how can we optimize our pipeline to make sure that we are meeting our latency and throughput SLAs? And that was another challenge. And finally, perhaps most critical one was relevance. So from few simple queries going into real-world production where users can ask anything, the question of relevance is very critical. And how do we handle queries that are not simple but are like complex queries? So there is something called multi-hop queries, where the user's intent is not only to look for one document or one chunk, but multiple documents in the vector database, or the query could be really ambiguous. They are still not certain what they are looking for, and they might just want to explore. So how do we handle different types of queries? So relevance is another factor that was there as a challenge for us. And this three-headed monster of cost, latency, and relevance is a core challenge in scaling the RAG pipelines. And this is not just my experience. I was doing a bit of research before this workshop to find out what people who are building RAG pipelines have been facing across the industry. And I came up with this survey from K2View, which is a reputed survey company, and they found out two things. So first is, what were the top challenges people were facing when deploying GenAI applications? So number one was cost, as you can see. And then more specifically to RAG system, what is the top concern when they have lots of unstructured documents in their pipeline? What's the most challenging part there? So most of the users there said it's scalability and performance. And if you look at the numbers, it's a huge concern for nearly half of the industry. I think in this survey there were about 2,000 people and from different companies, different sizes. And this data kind of confirms that the problem that I faced initially was not a niche problem. It's a problem that companies are facing still. And I might have forgot to tell you, but this survey was not from 2024. It's actually from May 2025. So it's pretty recent. And yeah, so how do we actually begin to tackle some of these challenges? Like, how do we tame this monster? Before we get into the practical strategies, one thing that I want to highlight is when we looked at the three-headed monster, it's important to kind of recognize that not all the heads or not all the problem areas are the same. We found that solving relevance is deeply personalized and an iterative journey. So it depends heavily on your use case, the quality of data that you have, where your data is stored. Is it stored in a vector database already, or is it in a NoSQL database? Like, do you already have chunks? And do you have some kind of metadata associated to your data? What is like compliance related concerns that you have with your data? So there are lots of nuances when it comes to like optimizing for relevance. And in our own pipeline, we went from something extremely simple that you saw in the first slide here to pretty close to what we have here. This is a picture from a research paper that came in 2024 where the authors looked into how different components of a RAG pipeline influence the overall relevance, and they provided a few best practices. Again, take that with a grain of salt. There are no universal best practices or no free lunch, but this is a good enough estimation of what a RAG pipeline in production optimized for relevance might look like. So there are lots of components that were added, and moving on from relevance, if we look at the other two heads, which were cost and latency, I believe that they are relatively much more universal than just a simple relevance problem. While every system is different, the underlying cost drivers are primarily the same. So you have memory, you have usage, you have memory usage, you have compute cycles, you have the tokens that the LLM is either generating or you're providing the LLM with the context, and that are pretty much the same for everyone. And the cause of high latency, like searching over massive indices or inefficient data processing, are also common architectural problems. And because these challenges of cost and latency are more well defined, there are powerful and generalized strategies we can apply to most RAG systems to see immediate improvements. And that is why for today's session, we are going to focus our energy on these more universal challenges than focusing on relevance. We'll put relevance aside for maybe another workshop and look at some of the strategies that can help you build RAG applications cheaper and faster. Okay, before I move on to the next session, here are a few articles that I would suggest people who are building RAG applications or are thinking about building applications to look into. These one from Uber and one from LinkedIn, different use cases, but they will give you a good enough picture of what a production scale RAG pipeline looks like, and they also talk about some of the challenges that they faced when building these systems in production. Okay. So now that we know about the challenges that we'll be focusing on in this workshop, what is a practical set of strategies that we can adopt to solve these challenges or to tackle these challenges? So I've broken down the whole RAG pipeline to three distinct phases. So and three distinct sequential phases. So number one is indexing. For those who don't know about indexing, it's basically the process of taking your documents, raw data, pre-processing it and storing it into some kind of a database. It could be a vector database, it could be a search engine. Nowadays, even traditional SQL-like databases like Postgres, they support a lot of search and vector retrieval kind of operations. When you store your data, it kind of creates an efficient data structure to then fetch these documents in real time when a user presents their query. So phase one is efficient data preparation and indexing. And the next phase is about retrieval. So when you have your data stored in an index, how do you actually retrieve the data from that index or from that database when a user provides you with a query? And the second phase is about how you can optimize the whole retrieval phase. And then the third phase is, now that you have collected the most relevant context for your user query, how do you actually pass that context to the LLM to then make a generation or a response, and then how you can also observe these responses, because often in a multi-component sequential pipeline like this, where you have multiple components, there could be one or more components that can be your bottleneck. So observing and identifying these components early on is really necessary. And that's why we'll also look at how observability of your pipeline can help mitigate some of these issues. So let's start with phase one. As I mentioned, in this phase, we have our documents that we want to index and store in a vector database or a search engine. For consistency, I'll just refer to that as an index from now on. And you can think about this phase as two separate steps. So first step is data preparation. So even before putting your data into a database or a search engine, you are doing some kind of data preparation. It could be simple data cleaning, or it could be chunking your documents into multiple chunks. It could be adding metadata to your chunks, which we'll see that it's really helpful later on. And then it also encompasses generating embeddings. So how many of you here are familiar with vector search? The concept of vector search. Okay, most of them. So yeah, so most of you here, you know about what an embedding is. So this phase also includes generating embedding. Then once you have your data in a good enough shape, you would want to store it or ingest it into an index from which it can be retrieved later on. And in this phase, you can optimize your index such that it saves you cost, and it's also faster than a vanilla index or a search engine that you have. So in this, we'll probably look at two optimization strategies. So number one is embedding quantization, and the other one is choosing the right ANN algorithm. And these are the techniques we'll also use in our hands-on workshop as well. So we'll look at how we can add additional metadata to our chunks, how that helps, and then also how can we quantize our embeddings, and also what's the role of different kind of ANN algorithms in a vector database. Okay, so the first one is pretty simple, I would say. So let's suppose that you have documents like these where you can have multiple attributes or multiple fields. So in this example, this is a collection or a table of cooking blogs. And it has fields like, or columns like title, description, author, date, category, etc. Now, when most people think about doing a vector search or doing a retrieval, their idea is, I'll have a user query, we convert that user query into embeddings, we have description or some kind of semantic field, we'll convert that into embeddings, and then we'll probably match those to return relevant results. That is a good enough place to start, but adding metadata is actually really helpful because then you can do things like filtering. So for example, let's say if a user in their query is specifically asking for cooking blogs about vegan chocolate from a specific author, let's say Alex Green, you can, before even doing any kind of vector search or vector retrieval, you can just do a filtering on all of your millions of documents and short it down or cut it down to only documents from Alex Green. And why is that helpful? Because vector computation, embedding computation is an expensive process, and even searching for similar documents given a user query is an expensive operation if you have millions and millions of documents stored in your index. So filtering is kind of an optimization that you can implement in your solution that will optimize your whole retrieval process.
Dealing with unstructured data, what happens if we don't have metadata? You recommend that we actually create them with LLM?
Yeah, so like there are different ways of creating external metadata, or like metadata to supplement the key fields. So for example, in this field, it's like description. Yeah, so you can use LLMs, or you could have metadata existing, but not maybe in the same table, but different tables. That you can then use to supplement the field, let's say description or title in this scenario. I would not recommend directly using an LLM for metadata creation because, again, depending on how many documents you have, it could be an expensive process. But usually there is some kind of fields or metadata that you can use to begin with to see if it's creating any value or not. Yeah. Yeah, and the second optimization in the indexing phase that I want to highlight is embedding quantization. I think all of you here are familiar with what an embedding is. And for those of you who are not, it's a array of floating points numbers, and then for a given query or for a given word, the array can contain thousands and thousands of values, when you multiply that by millions and millions of documents that you store, the size of your vector database or search engine can go from gigabytes to petabytes to terabytes to petabytes, which not only leads to more cost coming from memory, but also more cost coming from higher latency, because now your database has to search across all the millions of documents if in your database. And so quantization is the process of reducing the precision of those numbers in the array, similar to how some of you might be familiar with model quantization, where we quantize the weights of the model. Here we are quantizing the individual values within the embeddings. So if we go from, let's say, floating point 32 to an int 8, we can see a 4x reduction. And then if we go to more extreme cases like binary quantization, we get 32x savings in memory.
Want to go with reducing the embedding dimensions?
Yes, yes. So those are like, I would say, two approaches that you can take. Like either you can reduce the precision, or you can reduce the dimension. Not all models at this point supports what's called Matoksha or like MRL kind of embeddings, where you can like dynamically adjust the size. But like you can do this with all the models that you have, not only just for text models, but like for multimodal models as well. But yeah, that's another approach that you can adopt. And then
yeah, the scalar quantization, would it not cause any loss?
Yes.
Also, right?
Yeah.
Because there must be some best practices for this. Because
yes.
Today you do that, and tomorrow it might cause problems. Right? It might.
Yes. So I'm going to cover that in the coming slides. Yes. Yeah. Yeah. So just want to highlight like why would we want to do something like embedding quantization. As you can see here in the last column, that this is a screenshot from MTEB, which is a leaderboard for measuring the performance or the quality of embedding models. This is a subset only for text data, but you can see most of the models that are here, Gemini, Qwen, they have more than 1,000 dimensions in their embeddings. I think there is only one model in top 10 that is like less than 1,000. But just to kind of reiterate my point, when you have so many embeddings, dimensions, and then you have millions and millions of embeddings, the storage and also the latency will probably explode. This is another screenshot from the article from Hugging Face, where they kind of showcase what the cost would be for storing different numbers of embeddings. I think they used X2GD AWS instances, which is I think AWS's OpenSearch specific instances. As you can see here, if you have, let's say, hundreds of millions of embeddings, the monthly cost can go up to as high as $44,000 just for storage. It does not include costs that you need to run it for inference or any other kind of cost. Yeah, that is pretty much for more popular models as well. That kind of leads into how can we fix this, or how can we optimize this. So we can do embedding quantization, as I was saying earlier, and this picture kind of depicts the process of quantizing the embeddings. So you might have different values, as you can see here, and those values get converted into bits, 0 or 1. You can do scalar quantization. Here I'm just showing binary quantization, where you're going all to the extreme end of reducing the precision to just 1 bit. And you convert your floating point values into bits, and then you get a number, a binary number, which you can then convert. And you can use this for doing your similarity calculation instead of like the whole floating point numbers, which again might be more compute intensive and also lead to higher latency. But as you pointed out, that this conversion, similar to model quantization, is lossy. And if you try to do it yourself, which I've mentioned in the last slide as vanilla or naive binary quantization, you may not see good results in terms of relevance. You might see benefits in terms of cost and memory and latency, but you may not see benefits in terms of relevance. So your relevance might be impacted. And certain vector databases or search engine providers, they provide an optimized version of this quantization. In this slide, I will be talking about better binary quantization, which is an offering from Elasticsearch. And they basically fix 3 things. So first is error correction. So as we all talked about, that this conversion is lossy. And during this conversion, there can be multiple errors. So they kind of handle the errors out of the box in this conversion. And the next part is asymmetric quantization. So here, even though the vectors themselves are stored as single bits, the queries can be quantized to int4 or int8 to a higher precision. And that can significantly increase the search quality. And that adds no cost to storage, because your queries are not stored, they are coming in real time in inference, and those can be in higher precision, but your original document vectors can be in lower precision. And the last point is bitwise operation. So those of you who might be familiar with cosine similarity as a measure to calculate similarity between different embeddings. When you go to a bit level, you can optimize that even further. And bitwise operations are naturally more faster than doing individual values or individual dimension comparison for a floating point vector. And this leads to lots of speed and lots of reduction in memory. And actually, let's look at some of the numbers that Elastic has shared. So when you go from float to BBQ, which is binary quantization, for I think it's the last one is. Yes, yeah, so it's about 100 million vectors, which is not that unusual at a decent scale, especially when you consider multimodal vectors or different use cases. You can see that your memory goes from 409 gigabytes to approximately 14 gigabytes with better binary quantization. So it's pretty substantial reduction in memory. Also, in terms of indexing time, which is the time that it takes the database or the search engine to create the index from the documents that you provided or the embeddings that you provided, we can see that there's also a reduction in the index time. So again, if you look at 1 million vectors from Cohere V3 model, the indexing time went from 1206 to 681, approximately half. Even in like V2 different models, there's almost 25 to 50% reduction in index time. And last but not least, it's recall. So going back to the point of these conversions being lossy, yes, like even with this better binary quantizations or like other offerings of these optimized binary quantization from different providers, they are indeed lossy. But if you look at this graph, the bit quantization is in blue, and your full precision floating point is in red, which is here. You can see that around a latency of 3 milliseconds, which I believe is pretty low, they kind of match the recall for both binary quantization and the full floating point 32. So if your use case is such that your SLA is less than 3 milliseconds, which I believe, I'm not sure how many of you here have an SLA under 10 milliseconds for retrieval? Okay, so probably no one, which is good. So yeah, if your SLA is not under 3 milliseconds, I think better binary quantization or binary quantization provides a decent proxy for the recall that you can get with full floating point precision. Even if you have an extreme requirement for an SLA of less than 3 milliseconds, maybe you have a multi-component pipeline or like an edge use case or something else, then you can still see that like at approximately 1.5 milliseconds, these values are still comparable. But as I said, there's no free lunch, so in some extreme cases, you might still want to use like a scalar or maybe full floating point values. Okay, so the last thing that we are going to talk about in this phase is now you have your data ready, you have added metadata to your data sets, you have decided to use an optimized version of embeddings. So instead of like full precision embeddings, you're thinking about using an indate or maybe binary embeddings. But what about the type of index? So there are different types of indexing algorithms. Some of the popular ones that I've listed here are HNSW, IVF, and this is probably more recent. I think this came out in 2023, 2024 from NVIDIA. And they have different pros and cons. So HNSW, it's very popular. Most of the search engines, vector databases use some version of HNSW. Then there is, which is good for both speed and accuracy. Then there is IVF, which is for more memory constrained scenarios. So scenarios where you do not have large instances or you have really large data sets. And this is really efficient in terms of both memory and also in terms of latency. This is probably the fastest CPU-based algorithm that we have, but it suffers on recall, as we'll see later. And then the last one is Cagra, which is from NVIDIA. This has really high throughput, which means that you can support lots and lots of requests in parallel. And it has like very low latency and also can support large number of documents in an index. But the only downside with this is that this requires GPUs for indexing or for converting the documents into an index for searching. So as I said, all of these algorithms have their strengths and weaknesses. And they might be useful for different scenarios. So if your scenario is where you're okay with not getting the best recall, but you want to save a lot on memory and you want to save a lot on cost, and also you want like low latency, maybe IVF is a good option. If you have GPUs lying around and you can use GPUs in production for indexing, Cagra is a really good option. I think lots of vector databases, search engines now support most of these algorithms. And then there's this HNSW, which is kind of a good middle ground between IVF and Cagra. And this works on CPUs primarily as well. And more recently, there has been efforts from different vector databases and search providers to kind of fuse these algorithms. So right now, I know a lot of companies are working on doing indexing on GPUs and then converting into HNSW or IVF kind of embedding an index, so which gives you the benefit of cost and like latency at the same time. But those are again like pretty initial efforts and not proven yet, so I would not want to promote that. Okay, before we move on to the next section, there is this two reads that I would suggest again. One is the research paper from NVIDIA on Cagra, for those of you who might want to go into the detail of why this is so fast and like how this algorithms work, how this index work. This is a good paper to read. And then this is an article from Elastic, which is about comparing binary quantization, specifically their version of binary quantization, which is better binary quantization, with different types of quantization and how it kind of compares against different offerings. Okay, so moving on quickly to the next phase, which is like, okay, now you have your index or your data ingestion process optimized. But what can you do to make the retrieval process efficient and faster? And first, I want to highlight that most of the RAG pipelines that are in production have multiple stages, especially when we are dealing with a massive scale. And the reason for that is as you move along the stages, the models become more and more compute intensive. So maybe you want to start with a very simple BM25 or text-based retrieval, then you pass that on to a re-ranker, then you pass that on to an LLM, and then you can have multiple other subcomponents in the middle. But we can see a progression that as you move along the stages, the models become more and more complex. So if you provide lots and lots of documents to these models, your latency scales up. So the idea is that you start with, let's say, millions or even billions of documents. You use less complex but fast algorithm, let's say BM25 or even a hybrid search. Then you pass that the results from millions of documents to maybe, let's say, thousands of documents to a re-ranker, which re-ranks and gives you the 10 most relevant results given a user query, and then you pass, let's say, the top 3 or top 5 results from that re-ranking to an LLM. Yeah, this is kind of like a graph that shows different models and compares against each other, like re-rankers versus different models. So our goal here in each stage is to intelligently and efficiently refine the number of documents that we have, so that the documents that we are passing to the next stage are the most relevant documents, so that can like bring down our latency and we're not wasting time. And another disadvantage of passing lots and lots of documents is the models can get confused. I know there are some narratives online about RAG is dead because now all models have millions and millions token context window. But there have been a lot of research in this area that has shown that the promoted or marketed context window versus what is actually feasible and reliable are very different. And even if they are different and they meet your criteria, let's say you have 10,000 tokens that you want to pass, the compute cost and latency will still be an issue for you. So what can we do to kind of solve this problem in this stage? So 3 techniques. So one is filtered search, a bit of which we have already talked in the first phase. The second is using non-model based ranking algorithms. So I know we talked about using cross encoders or LLMs even as re-rankers, but you can still use non-model based algorithms if you have a good retrieval phase. And then the last part is result highlighting. So let's talk about each of them. So I think we have already talked about the hybrid search, filtered hybrid search piece. Going back to the same example, you have all these documents, you have metadata that you created for these documents. Now when you are doing retrieval in the first phase, you can filter down the documents by different categories or by rating or any other metadata that the user has provided in their query. So again, going back to
the question here, is there any way to do a smarter way of looking around the metadata? As opposed, let's say, if you have a query that the exact wording of the metadata is not there, or you have to do some sort of work to understand what data you have to look for, as opposed to vectorizing the whole database. You understand what I mean?
Yes, yes. So that goes back to a couple of slides. So like in a RAG, as you kind of iterate on your RAG pipeline, you'll have multiple components even before retrieval. So there could be a component like query classification or intent classification. And then there could be a component like entity extraction. So you have a query, now an LLM or a small model is trained to extract only the relevant entities. and then you kind of fetch the values of those entities and feed that into what we were seeing as a hybrid or like a filtered search scenario. Yeah, but that depends a lot on what kind of metadata you have and the cardinality of your metadata. So if, like, yeah, you have a column that has like values that are 99% the same, yeah, maybe that's kind of a good candidate versus like some column that has like very distributed values. So you have to kind of pick and choose which metadata field that you want to start with, begin with.
And when you say you have to do it, is that again the user have to change that, like
The developer, yes. When you're building the pipeline, you
it's
have.
not something that you automate, say that.
So you can actually automate this kind of query creation component as well.
That's not my question. Sorry, my question is doing this or letting Bert to do it. Like, what is the fine line that you say? Okay, up to this point, I'm gonna trust my developer to do it, or the whole thing. Let's say if there is a system, we deal with that system every 5 minutes. We deal with this issue. We don't want to vectorize the whole data set.
Yeah.
Like, where is that fine line for you?
So I would say I would start with something like a developer-based solution because I, as a developer, would know a lot more about the product and what kind of use cases that I can encounter. And then when I'm logging those results in the production traffic, I can then readjust this. And then if there is room that it can be automated, optimized by like the bird-like solution, then that would be an iterative process. But I would not start with a completely automated solution. Yeah.
Thank you.
One question, sorry. So on the phase 2 slide, you talked about some non-model rewriting
Yes.
approaches, right? So
Yeah.
can you give an example?
Yeah, I'm going to talk about it.
Okay, cool.
So so this is an example of like RF, which is a non-model based re-ranking approach. The idea of that is pretty simple. Let's say that you have a retrieval phase. In your retrieval phase, you're doing a hybrid search, which means that you are passing the same query to BM25 or lexical or keyword-based search system, and then you're also doing some kind of semantic searching, and then you get top 10 results or top 15 results from both of them. You see what's the ranking of each results in each of those lists or each of those streams, and then if a result has higher ranking in across both of those result streams, then the final ranking or the final score for that article or document would be higher. So as a concept, this idea is pretty simple, but the downside is that it's not personalized. The relevance might be lower than a more complex model-based approach. So that's why I recommend this to use in two scenarios. One is where you have like really low latency needs. You're just starting. You don't know a lot about how the system will scale. So starting with something like RF is a good option because it adds negligible load to your latency. And then the next thing is where you are using this as a first re-ranker. So even your re-ranking phase can have multiple re-rankers. So you start with the retrieval phase with millions of documents, you get thousands of documents, you pass those 1,000 documents to RF, you get maybe, let's say, top 100 documents.
Sorry to interrupt. Can you either speak into the podium mic or there's a handheld, because we're doing a record and it doesn't pick you up as well if you're not speaking into a mic.
Okay.
You want me to get you a handheld?
Yeah, I have it.
You have one. Okay, thank you. Turn it on. Yep. Thank you.
Yeah, so I would probably recommend this in these two scenarios for having really low latency needs or as a first re-ranker in your re-ranking phase. Now, an interesting component in this phase is a result highlighting. And this also goes back to the idea of passing the most relevant information down the stream to your components like LLMs or re-rankers. So if you have more input tokens, that's going to be more costly, high latency. How can you do that? So instead of just passing the entire chunk or instead of passing the entire document to your LLM, you can extract the most relevant portion from that document. So it could be just one line, it could be a couple of words, or it could be a couple of sentences in that chunk. And some vector databases and search engines like Elasticsearch they provide this functionality. So for example, let's say the query here was, where did Leonardo di Messi start his career? Yeah. And then you found out this document was the most relevant one because as you can see in the highlighted portion, it has the exact answer to what the question was asking. So instead of passing the whole document or the whole chunk, you can just pass this highlighted component here to the LLM, and probably it will look something like this, where this was the question, and let's say this was the full context, but only the green highlighted component here matters the most to answer the question. So you can just pass that on to the LLM instead of passing the whole document. And again, this helps with cost and latency because you are passing less tokens to the LLM for generation. And this is something that, as I said, some of these search engines or some of these vector database solutions provide natively, so you don't have to do something additional to activate this. And the way that this works is when they are calculating the score, either semantic score or lexical score, they can automatically identify how much each paragraph, or like you can set the limit, contributes to that score, and then fetch you that. We'll actually look at that in the workshop, hands-on workshop.
One question. So you said that the token consumption reduces, right? So,
Yes.
but we are making an additional API call to process the chunk and to highlight the chunk, right?
So that is part of the retrieval process. You're not making any additional call. This is not done by an LLM.
Okay.
These are natively supported by some of these search engines.
Okay. got
Yeah.
it.
So you're not making any additional call.
Excuse me, can I ask you a question?
Yes.
So we use the latest function called deep research from those LLM companies. And then the results of those deep research, they always have highlighted
Yeah.
in it. Is it the same thing?
So there are multiple ways.
Research use that?
Yeah, so there are multiple ways to do that. Actually, this is a screenshot from an article from Elastic. The article is titled RAG without AG. And then in this article, they are doing something similar where they're using Elastic to highlight the component or the answer or the critical part in the answer. But as I think someone asked, that you can even use LLMs to highlight that. So it depends, it's solution specific. But I highlighted this because there is no additional latency or cost associated to this. Yeah, so these are again some recommended reads about, one is about comparing different re-rankers. So the first one is a blog post that compares using cross-encoders, using RRF, using something called convex optimization, where you are, instead of giving equal weightage to BM25 and semantic search, you kind of put different weights. So maybe you say that, okay, keyword-based search is 90% more relevant than like semantic search, so you can assign different weights. And the other article is from Instacart, which kind of shows that shows how they are using technique like RF and convex re-ranking in production. And I think like in a follow-up article, they also talk about some of the improvements. So this is a good article to kind of read and understand how a production pipeline with RF in a rack setup might work. Okay, so down to the last phase very quickly. Now that we have retrieved and pinpointed the most relevant portions from our documents, how can we make generation faster? And as with other earlier phases as well, this is very subjective. Some people here might be using their own LLMs, some of them might be using OpenAI, some of them might be using open source models from, I don't know, Together or like some other providers. So there are lots, this space is pretty big, but again, just providing some solutions that are generalizable across different areas or different tech stack. So number one is, what happened? Interesting. Okay. Yeah, so number one is smart caching, or like caching the results of LLM. And this caching is twofold. So you can cache the prompts. Lots of model providers like Anthropic OpenAI, and even like AWS Bedrock recently introduced prompt caching. And then there is something called conversation caching, where you can cache the whole conversation history. And there are again lots of solutions for this as well. From you can even use Elastic or like any other kind of vector database for caching, or more recent solutions like Mem0 and other that are specific for caching the context or conversation history. One that I really like and I want to emphasize on is don't default to an LLM. I've seen a lot of use cases where like the use cases classification or intent detection, and there are lots of really good models that are available out there that you can use, or like if the model performance is not good, you can use LLMs for data generation and you can fine tune those models. That would lead to lower cost, they're easier to deploy, and then in some cases you may not even want a model. You just can use regex or some heuristics or logic to make a decision. So not every situation requires an LLM. And a really good example of this is, so this code actually uses something close to a regex for their evaluation. I think their example that they used, which I saw in a recent talk, was they wanted to know if the conversation tone is casual or formal. And I think initially they started with something like a LLM-based solution, but then with some additional heuristic, their final logic was if the first few words are capitalized, it's a pretty good signal that it's informal conversation, or if it has like exclamation marks or something like that. So it might not be 99.99% accurate, but like 85%. And like in production, most of the cases is like compromises or trade-offs. And yeah, the last one is like about designing, making fewer but richer calls.
Sorry, could you elaborate a bit on the conversation caching, like caching? Sorry, how are you able to pass the information along, like the state, if you're not sending it every time?
Yes, so as I said, there are different approaches and solutions to do this. So let's say you have a conversation that is active in a user session. You can store all the messages from that conversation into either a local object in the programming language, or you can just dump it to Elastic and do, or like any other kind of like search engine, and do like a retrieval for finding the most relevant chunks. Or there are more nuanced solution for that. But yeah, like you can do a lot of stuff with context conversation caching.
Thank you.
Okay, so that takes us to the last slide, and this is about observability. And I think this is a pretty good graph that I want to like show everyone. So I think like when people usually talk about observability and like metrics, they usually talk about, oh, what's the latency of my system, or what's the throughput for my system. And you can have a good throughput or low latency, but still miss SLOs or SLAs in your system. And this shows that. So in here we process 10 requests in 1 second, but like our SLA for, how many of you here know what TTFT or time to first token is? Okay, so time to first token and time per output token are two metrics that are used specifically for LLMs. Time to first token is given a request to an LLM, how quickly was the model able to generate the first token, and time per output token is the average across your generation. And this shows that you can have good throughput, but you might still miss these metrics for some of the responses, and that can have bad user experiences. So that's why observability is a good, not a good, but like an essential thing to do when you're building these applications, because you can then have a granular picture about your system to identify where the bottlenecks are across the system. Okay, this is a final kind of suggested read for today, which is again a blog post from LinkedIn where they mention about different production challenges specifically related to scaling that they encountered. Things like not using COT to building custom parsers. So I would highly suggest people building GenAI applications in prod to check this out. Okay, so yeah, this is a summary. Across all these phases, we can kind of do these different optimizations from non-model based ranking to finding golden snippets to caching and observability. Yeah, now let's get to coding. You can either scan this to get to the GitHub repo, or there's this URL link that you can follow to get to a Colab notebook.